All right, welcome again, students, and now we're going to do part 2 of periodic trends. If you remember, we commented that because the periodic table is so unique and because it's ordered and structured in such a incredible fashion, and it tells us so many different things, and we were specifically focusing in on the idea that it's organized according to energy levels, and that's what your rows correspond to, and within that you have your sub-levels, your S's and your P's kind of together, and your D's and your F's. Happen to be all coincidentally lumped together. And then it falls into categories where you have your metals on a certain side and your non-metals on another side. And all of that organization, we said again, points to the fact that you have a unique God who created this universe and brought everything into existence. And the periodic table is just yet another testament in science to that fact, unashamedly so. And as we begin, we want to continue with this idea that because of that unique arrangement, we have some periodic trends, some trends that come forth that we notice are in general are true about the elements. And we started with two. We started talking about atomic radius and talked about kind of the size of the atom and measuring the radius from the nucleus to the outermost electrons and why that occurs. And then we also talked about ionization energy, where you're removing an electron, and we were measuring, how much energy is required to remove the outermost electron. And both of them, hopefully you'll remember, were related to one another. Kind of the thing at the core, at the center, was what we called this electrostatic attraction. And I don't want you to forget that term. That is going to be key. And real quickly, just ask you a question. What is electrostatic attraction? That's right, it's the attraction between electrons and protons, or oppositely charged particles. And so we're going to continue to deal with that. That word kind of needs to stick in the back of your mind there as we continue to talk about these trends and why they are the way they are. We've got 2 more to go. So we did the first 2, and now we've got 2 more to go that we're going to deal with. And again, we need to remember that, okay, what was kind of at the core? Why did it require more energy to remove an electron from items on the right of the periodic table than items on the left? It had to do with, well, there was greater electrostatic attraction. Why? Because there were more electrons and more protons over there. And so because of that increased attraction, they held on to their electrons more tightly. And also, if you want to refer back to size, they were closer to the nucleus as well. Make sure that you don't mix these trends up. A common mistake that I see students make when asked about these trends is they'll understand the idea of atomic radius because they can kind of picture that, visualize that, and they understand the idea of size. But then they kind of take that idea of size and they place it upon the other trends. And that's not what we're talking about when we're talking about ionization energy or when we're talking about the next 2 that we're going to talk about. We're not directly dealing with the size of the atom. So don't mix those 2 up with any of the trends. All right, let's get started. Our first trend here, or I guess this will be our first we're going to talk about today, is what's called electron affinity. And electron affinity and ionization energy are kind of opposites of one another. So when you had ionization energy, we were trying to remove an electron, and we're seeing, well, how much energy is needed to remove? And that kind of goes counter to what atoms like to do. They don't like to add energy. They don't like to increase the energy of those electrons. So it kind of goes counter to what the direction that atoms normally like to move. Electron affinity is the opposite. The definition is it's the amount of energy released when you add an electron to a neutral atom. So if you think of it this way here, you're bringing in a new electron and you're forming a negative ion, and as it's doing that, as it's coming down, it's going to come down to ground state, so it's coming through those energy levels, and as it's coming through those energy levels, it's going to release energy, and the more energy released, the better. So there's kind of a trend and a pattern that falls out from this. There's going to be some atoms that have a high tendency to attract another electron. They like to attract another electron. And there's some atoms that don't like to attract electrons, and it's very difficult to add an electron to them. So that's really what we're looking at is if you wanted to boil this down, we're dealing with the likelihood that an atom is going to gain an electron. That's in a sense what we're measuring. Technically, we're measuring the energy that's released, but if you want to kind of put it in simple terms, we're measuring the likelihood that an electron is going to join an atom. So let's take a look at this. We already said it's the opposite of ionization energy, because ionization energy, you're forming a positive ion. With electron affinity, you're measuring, okay, what's it going to take to form a negative ion. And you've got kind of two things going on here. Oops, let me back that up here. It increases from left to right along a period. And it also decreases as you go from top to bottom on the periodic table. So your overall trend, and again this should be in your notes, your overall trend or your general trend of electron affinity is bottom left to top right, electron affinity increases. Now there is an exception here, and you do need to know the exception. So this is a little bit different. So again, bottom left of the periodic table to top right, electron affinity is increasing with the exception of the noble gases. And we'll talk about why do the noble gases, why are they kind of the exception? Why do they not want to gain an electron? So let's go ahead and move on to our periodic table. So what we're saying here is these guys here at the bottom, right here, oops, shouldn't have done that. Right here at the bottom, francium, radium, barium, cesium, these guys, they have a low electron affinity. In other words, they are not likely to gain an electron. They will not release a lot of energy, which is, again, what electrons want to do. They want to release as much energy as possible. So those guys at the bottom are not likely to gain an electron. As we move up here, all the way up to fluorine, oxygen, sulfur, chlorine, these guys right up here, these are going to have the highest electron affinity. In other words, they want to gain an electron. Now, we said the noble gases are the exception to the rule. And we're going to talk about those in just a second, so hang on to that. We're going to stay focused on the periodic table here. We're going to break it down left to right to start with, and kind of explain the why. So again, in your notes, that space that I left you, make sure that you're kind of writing down, left to right what's going on, top to bottom what's going on, because this will be something that I expect you to be able to explain. So left to right, what's happening? As I go, again, we'll use role 3 or energy level 3 there, starting with sodium, moving to chlorine. What's happening? Same thing. What's the difference between sodium and chlorine? It's the number of protons that they have. I'm increasing the number of protons. And of course, if I increase the number of protons, I'm also going to increase the number of electrons. And we said, as you add protons and you add electrons, what does that increase? It increases your electrostatic attraction. So again, the same explanation here. Well, okay, wait a minute now. How does that affect me attracting electrons? I can understand how that maybe affects the size or shrinks the size, but how does that affect my attracting electrons? Well, if my electrostatic attraction on the right side is greater, then it's going to be more likely that it's going to pull in a stray electron. Okay, so if I have a free-floating electron out there, or an electron from another atom that's just recently come loose, then I can attract that electron. Why? Because my electrostatic attraction is greater between the nucleus and my electrons there within a given energy level. Whereas over on the left side, I have fewer protons, and as a result, my electrostatic attraction is weaker, and therefore it's less likely that I'm going to attract an electron. And so in general, if you really want to break it down, and we'll kind of take a look at this a little bit later when we get to the next chapter dealing with things like bonding and whatever, we'll kind of break it down. And in general, your metals don't like to attract electrons. They have weak, if you want to say, electron affinity, whereas your nonmetals generally have a higher electron affinity, and they do want to attract electrons. So that's kind of where it comes into play when we start talking about things like bonding. That becomes kind of an important thing a little bit later. All right, well, what about the noble gases? I'm moving left to right. Why do I kind of stop at that seventh column there? Why do I not go to the noble gases, which are the far column on the right there with helium, neon, argon, krypton, so on? Hey, that was kind of funny. It rhymed there. That's not actually an element. So on is not actually an element, just so we know. But what's the deal with the noble gases? Because they are on the far right, so they do have more protons than electrons. So wouldn't the electrostatic attraction be greater? Well, technically, yes, it would, except for one thing. You'll notice, and we talked about this a little bit earlier, and at the end of last chapter, was we talked about valence electrons, and we talked about that you can have a maximum of 8. And you'll notice that all the valence electrons there in the noble gases there, I have 8. My shell, my valence shell is full. It's complete. And so I can't put in any more electrons. It would repel, okay, those extra electrons. So there's not a space for them to accept any more electrons. So when it comes to your noble gases, they're the exception. Why? Quite simply because on that right side, you've got a full valence shell. All right, what about top to bottom? What's going on? Well, top to bottom, we said that it's less likely. So these guys down here, things like cesium, barium, francium, these guys right here. Oops, I did it again. What's going on there? Those guys have a smaller or lower electron affinity. Why? Quite simply, again, it goes to electrostatic attraction. What's the difference between, let's say, hydrogen and lithium and cesium and francium? It's the amount of energy levels. I'm adding energy levels or shells, and each shell, remember, gets further from the nucleus. The further from the nucleus you are, the weaker your electrostatic attraction. And so as a result, if my electrostatic attraction at the bottom is very weak, it's going to be hard to pull in another electron. It's going to be very difficult because it's too far from the nucleus. Whereas the ones that are closer to the nucleus, like energy level 1, 2, or 3, it'll be a lot easier to pull in an electron. So that's why those at the bottom are not able to attract another electron. It's very difficult for them because the electrostatic attraction is very weak. All right, moving on, our last trend, and this one will be much simpler than the others. We're not going to go into as much explanation on these here, and it's called electronegativity. We will talk a lot about electronegativity in future chapters. Basically, it's the measure of the attraction between the nucleus and the valence electrons, and in particular, this is usually measured for atoms that are bonded in molecules. And so this is what kind of makes it difficult to break it down left to right, top to bottom. So we're not actually going to do that on the periodic table this time. So there's not going to be so much of an explanation as to why left to right, what's happening top to bottom, because usually this is dealing with atoms that are in a bond. And it was measured, this was first measured by a guy by the name of Linus Pauling, and he came up with the kind of scale of electronegativity. And it's kind of named after him, the Pauling scale of electronegativity. And it's basically a scale of 0 to 4. And if you look on your periodic tables, you'll see on the back of them, they have the measures of electronegativity. And really what you're measuring is the strength of an atom to pull electrons, those valence electrons, towards itself is what you're measuring. So think of a game of tug of war. So think of two people, and they're pulling on that rope. There's always going to be a winner. Somebody's going to be stronger than the other. Sometimes that game will be over real quickly. Sometimes it may take longer, but somebody's always going to win. Now think of those as two atoms tugging on those electrons. One atom is going to be stronger than the other, and that's what we're measuring when we're measuring electronegativity. The note, once again, the general trend is, as you look at the periodic table, bottom left to top right, electronegativity increases. So those at the top, things like fluorine, oxygen, sulfur, chlorine, those are generally your most electronegative elements. They have the highest. The ones down at the bottom left are your weakest, generally speaking. Now, the noble gases, again, are basically an exception to this, and the main reason why is because they don't bond. Now, in lab situations, they have been forced to bond for very short periods of time with things, and so some of them are kind of have a number that's given to them in terms of electronegativity. That is an artificial number, really, because they, in nature, don't bond. Now, you do want to know that your highest, I think this is important, your most electronegative element is fluorine, and your second is oxygen. Fluorine is pretty close to having a number of 4 in terms of its strength. So anything that bonds with fluorine, fluorine's going to pull those electrons towards itself. And that's kind of how what you're thinking of when you're dealing with that. And that is related to the whole electrostatic attraction and that does play a role in there as well, but we're not going to explain the how or the why as much today. So that's electronegativity.